Welcome to Science for Sleep. Tonight, we're about to dive into one of the universe's greatest mysteries, the speed of light. It's something we all hear about, something that we tend to take for granted. But when you stop and think about it, light isn't just fast, it's the limit. It defines how the universe operates, how space, time, and reality itself come together to form everything we know. But what if I told you the speed of light isn't just a measure of how fast light travels? What if it's something more profound? Something that defines the very structure of the universe, a limit that holds the fabric of existence in place. Tonight, we're not just going to talk about the speed of light, we're going to explore why light's speed is the ultimate limit in the universe. What if I told you that no matter what we do, no matter how advanced we get, we can never break that boundary? That's the mystery we'll uncover. The mind-bending secrets that physicist Richard Feynman uncovered that changed everything we thought we knew about the speed of light. What Feynman discovered will leave you questioning everything. Now, let's set the scene. The speed of light is famously known to be 299,792 kilometers per second. That's roughly 186,282 miles per second. But don't let the numbers get to you. It's not just about how fast light travels, but rather about what happens because of that speed. Think about it for a second. No matter where you are in the universe, whether you're standing on Earth or floating in deep space, light's speed doesn't change. It's the same everywhere. Whether you're moving towards the light source or away from it. Whether you're traveling through the vast expanses of the universe or sitting quietly on your couch, light's speed is constant. That's not just a random number. It's the foundation of how we understand space, time, and the very nature of reality. Think of it this way. If you were to stand at the edge of the universe and send a signal at the speed of light, it would always take the same amount of time to reach its destination, no matter the distance. It would take the same amount of time for that signal to travel to the nearest star, or all the way out to the furthest edge of the observable universe. Light is consistent, and it's the key to understanding everything in the universe. It's not just the speed at which things move, it's the limit. The boundary that holds the universe together defines causality and ensures that time and space behave as we experience them. But what makes light speed the ultimate limit? Why can nothing travel faster? You've probably heard of relativity and how it says that nothing can go faster than the speed of light, but do you know why? And more importantly, what did Richard Feynman discover that made us rethink everything about light speed? What did he uncover that will change the way you look at reality itself? This is where things get interesting. Richard Feynman, one of the greatest physicists of the 20th century, didn't just unravel the mysteries of light speed. He showed us something much deeper. Feynman's work was focused on understanding the quantum nature of light, but what he found didn't just apply to light, it applied to the universe. He introduced us to the idea that light isn't just a wave, nor just a particle. It's both at the same time. It's a concept that defies our understanding of reality. And that's where the real mystery begins. Light and its speed isn't just about how it travels. It's about how space and time themselves behave in response to light's constant speed. So, why can't anything travel faster than light? It's not just because of some law we've set. It's because the universe itself is built on light speed. Everything, from the way time flows to the way objects move through space, is connected to this speed limit. If anything could surpass the speed of light, it would cause the very fabric of reality to collapse. Causality would be broken. Imagine being able to send a message from the future to the past. Time itself would lose its structure. We'd be able to move through time like it was just another dimension to traverse. And that's not just an inconvenience. It would fundamentally destroy everything we know about how cause and effect work in the universe. You see, Feynman didn't just show us why the speed of light is the limit. He showed us that this limit is what makes the universe work the way it does. It's the very glue that holds space, time, and everything in between together. Without it, our entire understanding of physics and reality would crumble. The speed of light is the ultimate speed limit, but it's not just some arbitrary number. It's the boundary that defines how the universe operates. And if we could ever break it, everything we understand about space, time, and reality would change forever. So, now that we've introduced the mystery, let's get into how the story of light speed began, long before Feynman's discoveries. We'll go back to Galileo, who first tried to measure the speed of light in the 17th century, and we'll see how humanity's quest to understand light speed unfolded. But first, let's take a step back and appreciate why understanding light speed is so much more than just a scientific curiosity. It's the key to everything in the universe, and it's only just beginning to reveal its secrets to us. As we continue our journey into the mystery of light speed, it's essential to first explore the history of humanity's attempts to measure it. For centuries, the speed of light was a mystery. Scientists, philosophers, and mathematicians were fascinated by it, but it was almost impossible to measure accurately. It wasn't until the 17th century that the first serious attempts were made to measure light speed. The early attempts were nothing short of ingenious, even though they lacked the technology we have today. Let's start with Galileo, who in 1638 became one of the first to attempt measuring the speed of light. He was curious about how long it took for light to travel across space, so he designed a rather simple yet brilliant experiment. Galileo and an assistant stood on two distant hills, each holding a lantern. The idea was for Galileo to uncover his lantern and for his assistant to respond by uncovering their own lantern when they saw the light. The goal was to measure the delay between the two lights. Galileo thought that if light traveled at a finite speed, the delay in the light's arrival should be measurable. But, much to his frustration, there was no observable delay. The light appeared to travel instantaneously across the valley. Galileo, unable to detect any time delay, concluded that light must travel infinitely fast. But this wasn't due to a flaw in his experiment. The issue was that Galileo's instruments weren't capable of detecting such a tiny time delay. The speed of light was just too fast for the technology of the time. Despite his failure to measure the speed of light, Galileo's experiment laid the groundwork for future attempts. However, it wasn't until the 1670s that we began to get a more accurate understanding of light speed, thanks to Ole Rømer, a Danish astronomer. Rømer made a discovery that would change everything. In 1676, while observing the motions of Jupiter's moons, Rømer noticed something strange. The timing of Jupiter's moons seemed to be delayed when Earth was moving away from Jupiter in its orbit, and they were observed to appear earlier when Earth was moving toward Jupiter. At first, Rømer didn't know why this discrepancy existed, but after some thought, he realized that the light from Jupiter's moons had to travel longer distances when Earth was farther away from Jupiter, and shorter distances when Earth was closer. In other words, the apparent delay in the timing of the moons was caused by the finite speed of light. And for the first time, we had experimental evidence that light took time to travel across space. Rømer estimated the speed of light to be around 220,000 kilometers per second, which was remarkably close to the modern value of 299,792 kilometers per second. This discovery was a breakthrough and provided the first clear evidence that light does indeed travel at a finite speed. However, even though Rømer's discovery was groundbreaking, it took over 2 centuries before scientists were able to measure the speed of light with the precision we have today. In the 19th century, 2 key figures, Armand Fizeau and Léon Foucault, used more advanced methods to measure light's speed with much greater accuracy. In 1849, French physicist Armand Fizeau used a method that involved shining light through a rotating cogwheel. The idea was that light would pass through the gaps in the wheel and reflect off a distant mirror. The rotation speed of the wheel would determine how long it took for the light to travel to the mirror and back. From this, Fizeau was able to measure the speed of light to be approximately 313,000 kilometers per second, which was very close to the modern value. A few years later, Léon Foucault, also a French physicist, refined Fizeau's method. Instead of using a rotating wheel, Foucault used a rotating disc, which allowed for much more precise measurements. In 1862, Foucault used this technique to measure the speed of light as 298,000 kilometers per second, very close to the value we use today. These experiments laid the foundation for our modern understanding of the speed of light. But even with these advancements, we had no real understanding of why the speed of light was the limit. The answer to that question came in the early 20th century, when Albert Einstein and his theory of special relativity completely transformed our understanding of light's speed. Einstein's theory, published in 1905, brought a radical shift in how we viewed space and time. The second postulate of Einstein's special relativity stated that the speed of light in a vacuum is constant for all observers, no matter how fast they are moving relative to the light source. This was a game changer. Until Einstein's work, scientists believed that the speed of light might depend on the observer's motion. But Einstein showed that no matter how fast you're moving, the speed of light will always be the same: 299,792 kilometers per second. This revelation had far-reaching consequences. It meant that space and time were no longer separate entities. They were intertwined in what we now call space-time. And the speed of light wasn't just a speed limit for light itself. It was the speed limit for causality. This means that nothing, no object, no signal, no information could travel faster than light. If it did, it would break the fundamental structure of cause and effect. Time itself would start to behave differently, and the very laws of the universe would unravel. But Einstein's special relativity didn't just show us the speed of light's role in the fabric of space-time. It also led to another mind-bending consequence: time dilation. According to Einstein, as you approach the speed of light, time slows down. This means that if you were traveling at near light speeds, your experience of time would be vastly different from someone on Earth. What feels like a few days for you could be years for someone back home. This effect, known as time dilation, has been confirmed experimentally in numerous ways. And it's one of the most remarkable aspects of Einstein's theory. Now, while Einstein's theory changed everything, there was still one lingering question: could we ever break the speed of light? Einstein showed that nothing with mass could exceed light speed. But what about things like hypothetical particles, wormholes, or other exotic concepts in physics? Could these offer us a way to bypass the speed limit? As we continue our journey through the mysteries of light speed, it's time to explore one of the most mind-bending aspects of modern physics: quantum mechanics. This branch of physics deals with the tiniest particles in the universe. Things like electrons, photons, and other subatomic particles. But quantum mechanics isn't just a weird abstract concept. It's a crucial part of understanding how the universe works on the smaller scales. And it turns out that quantum mechanics also holds the key to understanding the limitations of faster-than-light travel. To begin, let's address a phenomenon known as quantum entanglement, one of the most bizarre and counterintuitive concepts in quantum mechanics. When two particles become entangled, their properties become linked in such a way that a change to one particle will instantly affect the other, no matter how far apart they are. Imagine two particles, one on Earth and the other on the other side of the galaxy. If we change the state of one particle, the other particle will instantly mirror that change. At first glance, this phenomenon seems to suggest that information can be transmitted faster than light, which would directly violate the principles of relativity. But here's the catch: quantum entanglement doesn't actually involve the transmission of any usable information faster than light. Instead, the correlation between the entangled particles happens instantaneously. No signal is actually sent between the two particles. This means that quantum entanglement doesn't break the light speed limit. It just challenges our understanding of how information works in the quantum realm. So, while entanglement may appear to defy logic, it still obeys the rules of special relativity, which means that faster-than-light communication remains impossible in the quantum world. The speed of light, while unbreakable in terms of transmitting information, is still safe in the world of quantum mechanics. Feynman, in his work with quantum electrodynamics, IQED, showed that even though particles interact in strange and mysterious ways, these interactions still respect the limits set by relativity. But let's move on to tachyons, which are even more exotic. Tachyons are hypothetical particles that, according to some theories, always travel faster than light. The term tachyon comes from the Greek word tachus, meaning swift or fast, and these particles have been postulated to travel at speeds greater than the speed of light. However, tachyons are not just any particles. They would have what's called imaginary mass. This means that their energy and momentum don't behave in the same way as normal particles. But here's the real kicker. Tachyons don't exist, at least not in any experimental evidence. They are theoretical particles, and their existence would require us to completely rethink the structure of relativity. If tachyons did exist, they would create a fundamental paradox because they would be able to travel backward in time, which would violate the principle of causality, the idea that cause and effect occur in a specific, predictable order. This is why tachyons are mostly regarded as speculative and are unlikely to ever play a role in practical physics. So, if tachyons are out of the question, what other ways might we potentially break the speed limit? The answer lies in even more speculative territory. Ideas like wormholes and warp drives. These concepts have captured the imaginations of physicists and science fiction fans alike, and while they might offer the potential for faster-than-light travel, they also come with huge theoretical hurdles. Let's first talk about wormholes. Tunnels through space-time that connect two distant points in the universe. If wormholes were real, they could provide an almost instantaneous path from one location to another. Think of a wormhole as a shortcut through the fabric of space-time itself, where you don't have to travel the long distances between galaxies, stars, or planets. Instead, you simply enter the wormhole, and you're instantly transported to the other side. The idea of wormholes was first suggested by Einstein and Nathan Rosen in 1935. Their Einstein-Rosen bridge was a theoretical solution to Einstein's equations in general relativity. Since then, the concept of wormholes has gained popularity, and physicists have studied the idea in great depth. In theory, wormholes could allow for faster-than-light travel. But there's a major problem: stability. For a wormhole to remain open long enough for anything to pass through, it would need exotic matter, a type of matter with negative energy density, to keep the wormhole's throat open. And unfortunately, we have no idea how to create or even detect negative energy. While wormholes could provide an escape route from the light-speed barrier, the lack of exotic matter and other technical challenges mean that they remain entirely speculative. As of today, no evidence exists that wormholes exist in the universe, and we don't have the technology to create them. The idea of warp drives, like the Alcubierre drive, is another theoretical solution to the problem of faster-than-light travel. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, involves creating a warp bubble that could move through space-time faster than light, while the object inside the bubble wouldn't actually be moving faster than light itself. The idea is to compress space in front of the spacecraft and expand space behind it, creating a bubble that carries the spacecraft at superluminal, faster-than-light speeds. This would allow us to travel vast distances without violating special relativity, since the spacecraft itself wouldn't actually be moving faster than light. Rather, the space around it would. The idea of a warp drive is fascinating, and it has gained attention in the scientific community, especially with the work of NASA and other organizations exploring advanced propulsion systems. However, there's a significant obstacle. Just like wormholes, and the energy requirements for creating a warp bubble are enormous, and we currently have no technology capable of producing the necessary energy to make this idea a reality. Moreover, exotic matter would also be required to stabilize the warp bubble, and, once again, we don't know how to create this exotic matter. As we've seen so far, the concept of the speed of light is more than just a scientific curiosity. It is a fundamental feature of our universe, shaping not only the way we understand the cosmos, but also the technologies we rely on in our daily lives. From the early work of Galileo to the groundbreaking theories of Einstein, the speed of light has been experimentally verified countless times, and its influence is present in everything we do, from navigation systems to communications. But how exactly does the speed of light impact our technology today, and how do we use its properties to navigate the modern world? Let's begin by considering the incredible accuracy with which we can now measure the speed of light. Thanks to advanced techniques developed over the years, we can measure light speed to a level of precision that Galileo or Einstein could never have imagined. In fact, the meter, the basic unit of length in the International System of Units, SI, is now defined by the speed of light. Specifically, the meter is defined as the distance that light travels in a vacuum in 1,299,792,458 of a second. This definition has made the speed of light one of the most accurately measured constants in science. But how did we get here? How did we transition from early attempts to measure light speed to defining fundamental units of measurement based on light's properties? In 1879, the physicist Albert Michelson conducted a series of precision experiments to measure the speed of light with greater accuracy than anyone before him. Using a device called an interferometer, which splits a beam of light and then recombines it after traveling along two different paths, Michelson was able to measure light's speed with remarkable precision. His work was groundbreaking, earning him the Nobel Prize in Physics in 1907. Michelson's experiment wasn't just important for confirming the speed of light, It was also crucial for confirming Einstein's theories of special relativity. The fact that light's speed is constant for all observers, no matter how they're moving, was an idea that Einstein introduced in 1905, and it was Michelson's experimental work that provided the evidence to support this claim. Over the years, Michelson's experiments have been refined, but his pioneering work laid the groundwork for the modern understanding of light's speed and its importance in physics. One of the most fascinating ways the speed of light impacts our everyday lives is through Global Positioning Systems, GPS. We often use GPS without thinking about the technology behind it, but it relies heavily on the principles of light speed and relativity. GPS satellites orbit Earth at an altitude of around 20,000 kilometers, and they move at speeds of about 14,000 kilometers per hour. At this speed and altitude, the clocks on board the satellites experience time differently from clocks on the surface of the Earth, are due to two relativistic effects: time dilation and gravitational redshift. Time dilation occurs because the satellites are moving at high speeds relative to the Earth's surface, which causes their clocks to run slower than clocks on Earth. This is a consequence of special relativity. Gravitational redshift happens because the satellites are farther from the Earth's gravitational field, so their clocks run slightly faster than those on the ground, a phenomenon explained by general relativity. The result of these two effects is that the clocks on the satellites tick about 38 microseconds faster than those on Earth each day. While this may seem like an insignificant amount of time, if it weren't corrected, it would lead to errors of up to 10 kilometers in GPS positioning. In order to keep the system accurate, the clocks on the satellites are pre-programmed to account for these relativistic effects. This means that our modern navigation systems, which allow us to find our location within a few meters anywhere on Earth, are actually built on our understanding of the speed of light and relativity. Without the constant speed of light and the precise measurements made over the years, GPS would not be the reliable tool it is today. Another major technology that relies on the speed of light is fiber optic communication. Fiber optic cables, which carry information as pulses of light, form the backbone of the internet, telecommunications, and television networks that we use every day. The speed of light in fiber optic cables is slightly slower than in a vacuum, around 200,000 kilometers per second, but it's still incredibly fast. This allows for high-speed data transmission over long distances. In fiber optic systems, light pulses carry digital information, such as emails, videos, and web pages, through glass fibers. As light travels through these fibers, it carries the encoded data with minimal signal loss and without interference, enabling ultra-fast communication across the globe. Without the constant speed of light in these systems, the internet would not be able to handle the amount of data we now rely on daily. The light speed limit ensures that information can travel across vast distances at near instantaneous speeds. Beyond telecommunications and navigation, the speed of light also plays a crucial role in space exploration. When we send spacecraft to distant planets or even other stars, we have to account for the time it takes for light to travel from Earth to the spacecraft, and vice versa. This delay, known as light travel time, becomes particularly significant when we send signals to spacecraft that are far beyond our solar system. For example, a signal sent to Mars takes about 13 minutes to travel one way, due to the average distance of about 225 million kilometers between Earth and Mars. When we send a signal to Jupiter, the delay is closer to 35 minutes. As spacecraft travel farther into the universe, the time it takes for signals to reach them increases exponentially. The farther the spacecraft is, the longer the delay, which presents unique challenges in communication and real-time operations. In the future, when we send missions to the outer planets or even interstellar space, light speed will be one of the greatest constraints. For example, Voyager 1, the farthest human-made object from Earth, is currently over 22 billion kilometers away, and it takes over 21 hours for a signal to travel from Earth to the spacecraft. This means that any mission to distant stars would face significant communication delays, possibly years for round-trip communication. While light speed might seem like a purely theoretical concept reserved for space travel and high-tech communications, it's woven into the very fabric of our modern world. The light speed limit governs how we interact with the universe in ways we don't even realize. Whether it's streaming videos from halfway around the world using satellite television or getting real-time updates on the weather, the speed of light is the unsung hero that makes it all possible. In computers, even though we don't physically see it, the speed of light plays a crucial role in how data is transferred through circuits and processors. The speed at which signals travel through electrical components is governed by the speed of light, affecting how quickly computers can process information. In essence, light forms the backbone of the modern digital age, allowing everything from cloud computing to global financial transactions to function seamlessly and efficiently. In medical technology, the speed of light also has a crucial role to play. MRI scans, CT scans, and X-rays all rely on electromagnetic radiation traveling at light speed to produce detailed images of the inside of the human body. The timing of these scans is essential for creating high-quality, accurate images. Without a solid understanding of light speed, doctors wouldn't be able to interpret these scans with the same precision. As we've learned, the speed of light is an ultimate limit for travel and communication in our universe. It shapes the very fabric of how we perceive space and time. But in the world of quantum mechanics, things start to get weird. Quantum physics challenges many of our traditional ideas about reality, offering the possibility of phenomena that seem to defy the laws of classical physics, including the speed of light limit. One of the strangest concepts in quantum mechanics is quantum entanglement. Entanglement occurs when two particles become so deeply connected that the state of one particle instantly affects the state of the other, regardless of how far apart they are. Distance seems to have no effect on this connection. If you change one particle, the other responds instantaneously. This is true even if the particles are light years apart. At first glance, this seems to violate the speed of light limit. How could information travel faster than light? In theory, this looks like a direct contradiction to everything we know about space-time and relativity. However, it's important to understand that quantum entanglement doesn't actually transmit information at faster than light speeds. While the particles' states are correlated, no usable information is being transferred faster than light. What's happening is a kind of instantaneous correlation, not communication. So, despite the apparent weirdness of entanglement, it doesn't actually break the speed of light limit. This demonstrates that quantum mechanics and relativity can coexist, but they don't allow for faster-than-light communication. But what about the idea of tachyons, particles that are theoretically faster than light? Tachyons are hypothetical subatomic particles that were first proposed in the 1960s as a solution to certain equations in quantum field theory. Tachyons are thought to have imaginary mass, which makes them behave very differently from the ordinary particles we encounter. Unlike normal particles, which can never reach the speed of light, tachyons would always move faster than light, even from the moment they're created. The problem with tachyons, however, is that they are still purely theoretical. Despite extensive research, there's been no experimental evidence to suggest that tachyons actually exist in the real world. And even if they did, they would create some serious problems. For example, tachyons could potentially allow for time travel, violating the fundamental principle of causality, the idea that cause must precede effect. Imagine traveling back in time and altering the past. This could create paradoxes and alter the very course of history. So, while tachyons are fascinating to think about, they don't offer a practical solution to faster-than-light travel. Let's take a step further into the realm of theoretical physics and explore the possibility of wormholes. Wormholes are sometimes referred to as Einstein-Rosen bridges, after the physicists Albert Einstein and Nathan Rosen, who first proposed them in the 1930s. In essence, a wormhole is a shortcut through space-time, a tunnel that connects two distant points in the universe, bypassing the vast distances in between. If wormholes existed, they could theoretically allow for instantaneous travel between two locations that would otherwise take millions of years to reach. The concept of wormholes is incredibly enticing for the possibility of faster-than-light travel. Imagine being able to enter a wormhole and emerge at the farthest reaches of the universe in the blink of an eye. However, there are major hurdles to overcome. Wormholes are purely theoretical, and no experimental evidence has been found to suggest that they actually exist. Even if they do exist, stabilizing a wormhole so that it remains open long enough for us to pass through would be an enormous challenge. According to current theories, wormholes would require exotic matter, a form of matter with negative energy density, to keep the tunnel open. Unfortunately, we don't have the technology or the understanding of negative energy to make this possible. Without exotic matter, wormholes would collapse too quickly for anything to pass through. The idea of a warp drive is another fascinating theoretical concept that could offer a path for faster-than-light travel. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, involves a warp bubble that could allow a spacecraft to travel faster than light. Rather than moving the spacecraft itself at faster-than-light speeds, the idea is to warp or distort space-time around the spacecraft. By contracting space in front of the ship and expanding it behind, the ship could effectively ride a wave of distorted space-time, traveling faster than light without ever violating the rules of special relativity. In theory, the Alcubierre drive could allow for interstellar travel, with a spacecraft crossing vast distances without exceeding the speed of light in the traditional sense. The trick is that space-time itself moves faster than light, not the spacecraft. This could potentially make travel to distant stars like Alpha Centauri a reality. But just like wormholes, the energy requirements for an Alcubierre drive are enormous. Creating the required warp bubble would require vast amounts of negative energy, and we currently have no way of producing or harnessing such energy. Until we figure out how to manipulate space-time on this level, the Alcubierre drive remains purely theoretical. As we've explored, the speed of light is not just a concept we study in theoretical physics. It's the fundamental boundary that governs the very nature of space and time. Understanding this limit is not just for scientists. It shapes the technology we use every day. From communication to navigation, the speed of light is embedded in the technological systems that define our modern lives. Let's now take a closer look at how light speed impacts real-world experiments and drives innovations in technology. One of the most direct ways the speed of light affects our daily lives is through the Global Positioning System, GPS, which we use to navigate the world. GPS satellites orbit Earth at altitudes of about 20,000 kilometers, and they travel at speeds of around 14,000 kilometers per hour. At these speeds, the clocks on board the satellites experience time differently from those on the ground. The reason? The relativity of special relativity and general relativity. According to special relativity, time slows down for objects moving at high speeds. In this case, because the satellites are moving at such high velocities, their clocks tick slightly slower than those on Earth. This is the time dilation effect. On the other hand, general relativity predicts that time moves slightly faster in weaker gravitational fields. Since the satellites are farther from the Earth's gravitational pull, their clocks tick faster compared to clocks on the surface of the Earth. Together, these effects cause the clocks on the satellites to tick about 38 microseconds per day faster than those on the ground. While this may seem like a tiny difference, without correcting for these relativistic effects, GPS systems would experience errors of up to 10 kilometers in positioning accuracy. In other words, without an accurate understanding of the speed of light and relativity, the GPS systems that guide our cars, our smartphones, and our planes would be practically useless. Every time you use a GPS app to navigate the streets, you're relying on light's speed to help you find your way. The GPS system functions because we account for light travel time, and relativity ensures that the signals from satellites reach us in real time, with corrections for relativistic effects. This is just one example of how the speed of light is not just a theoretical idea. It's critical to the precision and accuracy of the technology we depend on. Another major technology that relies on light speed is fiber optic communication, the system that powers the internet, television, and telecommunications around the world. Fiber optic cables use light pulses to carry information. These cables are made from glass fibers, and light travels through them at slightly slower speeds than it would in a vacuum, around 200,000 kilometers per second. The speed of light in fiber optic cables is critical because it allows information to travel at the incredible speeds we're accustomed to today. When you send an email, stream a video, or use social media, the data is transmitted through fiber optic cables carried by light pulses. The fast speed of light is what enables us to send data across the globe almost instantaneously. Without the ability to transmit light signals at high speeds through these fibers, our digital world would slow to a crawl. It's not just about internet speed. It's about how the very infrastructure of the internet is based on the physics of light. Fiber optics are a key technology that makes global communication possible, connecting continents and enabling our modern way of life. The speed of light also plays a crucial role in space exploration. When we send spacecraft to distant planets, moons, or even other stars, we must consider the time it takes for light to travel to and from the spacecraft. This delay, known as light travel time, becomes especially important as we venture further into space. For example, consider NASA's Voyager 1 spacecraft. As of today, Voyager 1 is the farthest human-made object from Earth, traveling over 22 billion kilometers from our planet. It takes over 21 hours for a signal to travel from Earth to Voyager 1 and back. The communication delay is so significant that NASA engineers can only send commands and receive data from the spacecraft with a time lag of over a day. As space exploration extends farther out, whether it's to Mars, the outer reaches of the solar system, or beyond, this light travel time will be a major factor. For instance, a signal sent to Mars, which is about 225 million kilometers away from Earth, takes around 13 minutes to travel. That's 13 minutes of delay before any communication happens, making it impossible to operate rovers or satellites on Mars in real time. At the speed of light, communication with deep space probes will always be delayed, and this will be the largest barrier to true real-time control of space missions. As missions venture further into space, light speed will be an ever-present constraint, requiring new strategies for autonomous spacecraft and robotic exploration. In addition to space exploration and telecommunications, the speed of light plays a significant role in medical technologies. MRI scans, CT scans, and X-rays all rely on electromagnetic radiation, light waves, to generate detailed images of the human body. The timing of light's travel through the body is essential for creating accurate images. For example, in MRI, magnetic resonance imaging, radio waves a form of electromagnetic radiation, interact with hydrogen atoms in the body. The resulting signals are then processed into detailed images of the body's internal structures. The precision required in MRI imaging depends on the speed at which electromagnetic signals travel. If we didn't have such a clear understanding of light speed, these systems would lose much of their accuracy. Similarly, in X-ray imaging, the speed at which X-rays travel through the body determines how quickly images are captured, allowing doctors to observe broken bones or diagnose illnesses. The reliance on light to create clear, high-quality images means that speed is a critical factor in modern medical diagnostics. In the realm of computing, light's speed plays a role in how data is transferred and processed. While computers rely on electrical signals to transmit information, the speed at which these signals travel is influenced by the speed of light. The ability of electrons to move through circuits depends on light speed limitations, affecting how fast processors can handle information. In the future, the development of quantum computers might bring even more fascinating implications. Quantum computers, which leverage the principles of quantum mechanics to process information, could someday achieve mind-boggling speeds, operating at speeds far beyond what today's classical computers can handle. While this technology is still in its infancy, understanding the speed of light and relativity will be crucial in shaping the development of next-generation computing technologies. As we've explored the fundamental limitations set by the speed of light, we now venture into the realm of quantum mechanics, where the boundaries of space and time become even more elusive and unpredictable. Quantum mechanics deals with the fundamental particles and forces that make up the universe, and while its effects may seem strange or counterintuitive, they offer insights into how we might one day challenge the speed of light. At the heart of quantum mechanics lies a concept known as quantum entanglement. Entanglement occurs when two particles become so intricately linked that the state of one particle instantly affects the state of the other, no matter how far apart they are. Imagine two particles, one on Earth and the other at the edge of the observable universe. According to classical physics, a change in one particle's state should affect the other with a time delay corresponding to the distance between them. But in the quantum world, entangled particles defy this logic. A change in the state of one particle will immediately affect the other, regardless of the distance. This instantaneous connection between particles might seem to suggest that information can travel faster than the speed of light. But this phenomenon doesn't actually allow for faster-than-light communication. What's happening here is not the transmission of information, but rather a correlation between the particles. No usable signal is transmitted between them. This is why quantum entanglement does not break the speed of light barrier. It challenges our understanding of causality, but doesn't allow us to send information faster than light. While quantum mechanics introduces some mind-bending concepts like entanglement, it still respects the speed of light limit in terms of actual information transmission. The speed of light is still the ultimate limit in the universe when it comes to sending signals or data. which is why the quest for faster-than-light travel remains rooted in theoretical physics. Let's move on to explore one of the most speculative ideas in the search for faster-than-light travel: the concept of tachyons. Tachyons are hypothetical particles that, according to certain theories, always travel faster than light. The term tachyon comes from the Greek word tachys, meaning swift. These particles were first introduced in the 1960s to help explain certain equations in quantum field theory. Tachyons are theorized to have imaginary mass, which means their energy and momentum behave very differently from ordinary particles. In theory, tachyons could travel faster than light. But there's a major catch. No experimental evidence has been found to support their existence. In fact, the idea of tachyons brings with it significant paradoxes and issues with causality. For instance, tachyons, by their very nature, could allow for time travel, which would violate the principle of cause and effect that governs the universe. Imagine the chaos that would ensue if information could be sent into the past before it was even created. This breaks causality and creates a logical paradox. Because of these issues, tachyons remain firmly within the realm of speculation, a theoretical concept that doesn't have practical application. But just because tachyons are a theoretical idea doesn't mean that all hope is lost for breaking the speed of light barrier. The realm of space-time manipulation presents some intriguing possibilities for faster-than-light travel. Let's talk about wormholes, another theoretical concept that offers the potential for instantaneous travel across vast distances in the universe. Wormholes are sometimes referred to as Einstein-Rosen bridges, after the physicists Albert Einstein and Nathan Rosen, who proposed them in the 1930s. Essentially, a wormhole is a tunnel-like structure that connects two separate points in space-time. Picture it like a shortcut, where instead of traveling the long distance across space, you enter a wormhole and emerge instantly at a distant location. If wormholes could exist and be stabilized, they could allow for faster-than-light travel, effectively bypassing the speed of light limitation. While the idea of a wormhole sounds like science fiction, it has a solid foundation in general relativity. The equations of relativity allow for the existence of these tunnels through space-time. But there's a catch. They require exotic matter, a form of matter with negative energy density, to keep the wormhole open. Theoretically, wormholes could be formed, but exotic matter is still purely speculative, and we have no way to create or stabilize a wormhole in real life. Even if wormholes did exist, they would likely be highly unstable. The energy required to open and maintain a wormhole would be immense, and without exotic matter to stabilize it, the wormhole would collapse, preventing anything from traveling through it. This makes wormholes a fascinating idea in theoretical physics, but as of now, they remain an unrealized concept, one that challenges our understanding of space-time and the speed of light. Now, let's turn to another theoretical concept in the quest for faster-than-light travel: the Alcubierre drive. Proposed by physicist Miguel Alcubierre in 1994, the Alcubierre drive is often referred to as a warp drive. The idea behind the warp drive is to create a bubble of space-time that moves faster than light, while the spacecraft inside the bubble remains stationary relative to the bubble itself. In other words, the spacecraft wouldn't be moving faster than light. Instead, the bubble of space-time that it's contained within will be moving faster than light, carrying the spacecraft along with it. The Alcubierre drive doesn't violate special relativity because the spacecraft itself is not moving through space faster than light. Instead, the space around it is manipulated to create a faster-than-light journey. This concept offers a fascinating way to travel to distant stars and galaxies without violating the laws of physics as we understand them. However, just like wormholes, the energy requirements for creating such a warp bubble are astronomical, and we would need exotic matter, something with negative energy density, to make this idea a reality. The notion of a warp drive also faces significant practical challenges. We have no current way of producing negative energy, and the amount of energy required to distort space-time on such a scale is far beyond anything we could generate with today's technology. Nonetheless, the Alcubierre drive is a thrilling concept that offers a potential path to faster-than-light travel, even if we are still far from making it a reality. While the theoretical concepts we've explored, such as warp drives, wormholes, and tachyons, are fascinating and push the boundaries of our imagination, we still face the harsh reality of the speed of light limit when it comes to actual space exploration. In practical terms, the challenge of traveling beyond the solar system and reaching other stars remains a daunting one. The speed of light governs the very fabric of space-time, and as we push farther into the cosmos, we are continually constrained by the limitations of our current propulsion technologies. Let's consider the distances involved in space travel. The closest star to Earth, Proxima Centauri, is approximately 4.24 light-years away. That means that even traveling at the speed of light, it would take 4.24 years to reach it. But with current spacecraft technology, we're nowhere near that fast. For example, NASA's Parker Solar Probe, which holds the record as the fastest human-made object, travels at about 700,000 kilometers per hour. That's roughly 0.064% of the speed of light. At that speed, it would take over 6,700 years just to reach Proxima Centauri. And that's just one of the closest stars. The rest of the galaxy is even farther out, making interstellar travel appear to be an impossible feat with our current technology. The reason for this limitation is tied to energy. As we learned from Einstein's theory of special relativity, the closer an object gets to the speed of light, the more energy it requires. To accelerate a spacecraft to near-light speeds, we would need an astronomical amount of energy, far beyond anything we can produce today. And even if we could generate this energy, the spacecraft would still be limited by the speed of light barrier, meaning that no matter how advanced our technology becomes, we would always be bound by this ultimate limit. While space exploration is one of the greatest achievements of humanity, the practical limitations of long-distance travel remain a significant hurdle. Let's take a closer look at the current state of space missions and the challenges we face as we venture deeper into the cosmos. NASA's Voyager 1 spacecraft, launched in 1977, is the farthest human-made object from Earth, currently traveling at over 17 kilometers per second. Yet, it is only now leaving the solar system. And even at this incredible speed, it is taking over 21 hours for a signal to travel from Earth to the spacecraft. Voyager 1 has traveled over 22 billion kilometers since its launch, but it's still not even close to the nearest stars. At its current pace, it will take over 70,000 years to reach Proxima Centauri, far beyond the lifespan of any human mission. For future space missions, the speed of light remains the ultimate limiting factor. Even sending probes to the outer reaches of the solar system takes years, and the communication delays make it impossible to operate spacecraft in real time. Instead, mission planners must work with autonomous systems to make decisions for spacecraft far beyond our reach. These limitations are even more apparent when we think about the future of human exploration. While sending a robotic spacecraft to Mars or beyond may take several months or years, sending humans to those distant worlds will require enormous advances in technology, life support systems, and propulsion methods. At present, the most common propulsion technology used in space travel is the chemical rocket engine. This technology has been incredibly successful for missions within our solar system, including sending astronauts to the Moon and rovers to Mars. However, chemical rockets are far from efficient when it comes to long-distance space travel. The problem lies in fuel efficiency. The faster a spacecraft moves, the more fuel it needs, and the more fuel it carries, the more mass it adds to the spacecraft, meaning it becomes harder to accelerate. To put it simply, chemical rockets are good for short-range space missions, but they are not suitable for interstellar travel. We need a propulsion system that can provide more efficient and sustainable energy to accelerate spacecraft to speeds that could make interstellar missions feasible. This is where concepts like the ion engine come into play. Ion propulsion is much more efficient than chemical rockets and has already been used in missions like NASA's Dawn spacecraft, which traveled to the asteroid belt. Ion engines use electricity to ionize a propellant, creating charged particles that are expelled at extremely high speeds to generate thrust. While ion engines are much more efficient than chemical rockets, they provide low thrust, which means they take much longer to accelerate a spacecraft to high speeds. For now, ion engines are best suited for shorter missions, like exploring the outer solar system. But they are still far from offering a solution for faster-than-light travel. One exciting possibility for the future of space propulsion is the nuclear fusion engine. Fusion, the process that powers the sun, has the potential to provide massive amounts of energy with much greater efficiency than chemical or ion engines. If we could harness fusion for space travel, it could dramatically reduce the travel time to distant planets and even stars. However, nuclear fusion technology is still in its infancy, and we are still decades away from being able to use it for propulsion in space. Looking ahead, the future of space exploration is exciting and full of possibilities, but interstellar travel is still a long way off. For the time being, we will focus on exploring our solar system, particularly Mars and the outer planets, as well as investigating the mysteries of distant exoplanets and black holes. However, even with current technology, missions to Mars and other planets are fraught with challenges. It's not just about getting there, it's about keeping astronauts alive, providing them with sustenance, and ensuring they have reliable communication with Earth. NASA's Artemis program, which aims to return humans to the Moon and establish a sustainable human presence there, will serve as a key stepping stone toward interplanetary and interstellar travel. By developing the necessary technologies to sustain life on the Moon and Mars, we can begin to understand the challenges of long-term space travel and start laying the foundation for missions that will take us beyond our solar system. Meanwhile, private companies like SpaceX are developing new spacecraft and innovative propulsion systems that could pave the way for human missions to Mars and other planets. Starship, SpaceX's next-generation spacecraft, is designed to carry humans to Mars and beyond. And while it may not be capable of faster-than-light travel, it represents a significant leap in our ability to explore deep space. As we continue to push the boundaries of human exploration, we find ourselves confronted with the ultimate question: can we break the speed of light? It's a question that has intrigued physicists, engineers, and dreamers alike for centuries. While the speed of light remains the unshakable limit set by Einstein's theories of relativity, humanity's ingenuity has never been held back by boundaries alone. Theoretical physicists have long proposed ideas for how we might circumvent the light speed limit, and emerging technologies are beginning to offer us new tools to navigate the cosmos faster and more efficiently. So, while we may not be able to break the speed of light in the traditional sense, we can explore theoretical solutions, investigate new propulsion methods, and begin developing technologies that allow us to bypass the light speed barrier in ways we never imagined before. The concept of faster-than-light, FTL travel, has captured the imagination of scientists and science fiction writers for generations. If we are ever to break the light speed barrier, we must look beyond conventional methods of propulsion and instead turn to exotic ideas that could challenge our understanding of physics. Let's take a closer look at some of the most exciting and speculative theories for FTL travel. One of the most well-known theoretical solutions for FTL travel is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. The Alcubierre drive, often referred to as a warp drive, involves creating a bubble of space-time that moves faster than light. Essentially, the spacecraft itself wouldn't be moving faster than light. Rather, the space around the spacecraft would be manipulated to move faster than light, carrying the spacecraft along for the ride. This warp bubble would compress space-time in front of the spacecraft and expand it behind, creating a region of space that the spacecraft could ride through at superluminal speeds. Importantly, the Alcubierre drive doesn't violate Einstein's theory of relativity because it's not the spacecraft itself moving faster than light. It's the space-time surrounding it that's moving. In this model, the spacecraft stays within the bubble, so it doesn't experience the relativistic effects of traveling faster than light. However, there are significant challenges to this idea. First, the energy requirements are staggering. To create a warp bubble, we would need an enormous amount of energy, likely far beyond anything we can currently generate. Additionally, we would need to find exotic matter that has negative energy density, to keep the bubble stable. So, while the Alcubierre drive is an intriguing concept, it remains purely theoretical for now. The technologies and energy sources required to make it work are far beyond our current capabilities. Another exciting possibility for FTL travel involves the use of wormholes, tunnels through space-time that connect two distant points in the universe. The concept of a wormhole is often compared to folding a piece of paper so that 2 points on opposite ends touch. In theory, a wormhole would allow an object to travel between the 2 points almost instantaneously, bypassing the vast distances of space. Wormholes are allowed by the equations of general relativity, and they provide a possible shortcut through the fabric of space-time. However, the practicalities of creating a stable wormhole are still unknown. For a wormhole to be traversable, it would require exotic matter with negative energy to keep it open. Without this exotic matter, the wormhole would collapse before anything could pass through. Stabilizing a wormhole would likely require technologies we currently don't have, and we have no evidence that wormholes exist in the universe. Yet, despite the challenges, the wormhole concept remains one of the most fascinating ideas in theoretical physics. If we could create and stabilize a wormhole, it would revolutionize space travel, allowing us to explore distant galaxies almost instantaneously. Quantum mechanics introduces another strange and speculative idea in the quest for faster-than-light travel: quantum tunneling. This phenomenon occurs when particles pass through barriers that would normally be impenetrable in classical physics. At the quantum level, particles can tunnel through space-time itself, effectively bypassing obstacles that would stop larger objects. While quantum tunneling is a well-known phenomenon in subatomic particles, some theorists have speculated that it could be applied on a larger scale to allow objects to pass through space-time barriers. However, quantum tunneling at the macroscopic level is far from achievable with current technology, and it remains an open question as to whether it could ever be applied to faster-than-light travel. Despite its speculative nature, quantum tunneling offers a glimpse into the potential of quantum mechanics to shape the future of space travel. If we could harness this effect, we might find a way to bypass the constraints of light speed. While faster-than-light travel remains theoretical, humanity has made remarkable strides in achieving near-light speed with current propulsion technology. The challenges of light-speed travel are immense, but near-light speed missions are already on the horizon. These technologies could pave the way for interstellar exploration, even if we can't yet break the light speed limit. One of the most promising technologies for near-light speed travel is nuclear fusion propulsion. Nuclear fusion, the process that powers the sun, could provide nearly limitless energy. Unlike chemical rockets, which burn fuel and expel exhaust gases to generate thrust, fusion propulsion would harness the power of atomic nuclei fusing together to release vast amounts of energy. Fusion propulsion offers an incredibly efficient method of space travel, and it could enable spacecraft to reach significant fractions of the speed of light. In fact, if fusion propulsion were viable, we could potentially send spacecraft to the outer reaches of the solar system in a matter of months rather than years. The technology is still in its early stages, but companies like Helion Energy and Tokamak Energy are working on creating fusion reactors that could one day power spacecraft. While we're still far from building fusion-powered spacecraft, the concept remains a key area of research. If successful, fusion propulsion could revolutionize space exploration and take humanity closer to the stars. Another potential solution for faster space travel is antimatter propulsion. Antimatter is the opposite of matter. For every particle of matter, there is an equivalent particle of antimatter. When matter and antimatter collide, they annihilate each other in a release of energy. This process releases more energy than any other known reaction, making it incredibly efficient. In theory, antimatter propulsion could allow spacecraft to reach a significant fraction of the speed of light. However, producing and storing antimatter is a significant challenge. At present, antimatter can only be created in small quantities in particle accelerators, and storing it without it reacting with regular matter is another unsolved problem. While antimatter propulsion remains speculative, it's one of the most promising ideas for high-efficiency space travel in the distant future. Breakthrough Starshot is a project aimed at sending tiny probes to Alpha Centauri, our nearest star system, at a speed that could be 20% the speed of light. The idea is to use laser beams to accelerate small lightweight probes equipped with light sails. The project aims to send these probes on a journey to Alpha Centauri, which is 4.24 light-years away, within decades, a far shorter time than current propulsion methods would allow. While Breakthrough Starshot won't reach faster than light speeds, it represents a leap forward in interstellar exploration. Using light sails driven by powerful lasers, these probes could travel to distant stars at speeds previously thought impossible. While we are still in the early stages of this project, it provides a glimpse into the future of space exploration and the potential to explore other star systems. The speed of light remains the ultimate limit in the universe. While many theoretical ideas, such as the Alcubierre drive, wormholes and tachyons, provide exciting possibilities for faster-than-light travel, we are still far from making these ideas a reality. However, as we push the boundaries of physics and technology, we are beginning to see the first steps toward overcoming the speed of light limit. Emerging technologies like fusion propulsion, antimatter engines, and light sail-driven missions are bringing us closer to interstellar exploration. And while we may never break the speed of light, these advancements show that humanity is determined to push the boundaries of space travel and explore the stars. The future of space exploration is bright, and even though the speed of light may remain the ultimate limit, humanity will continue to strive for new solutions that allow us to explore the farthest reaches of the cosmos. As humanity imagines traveling beyond our solar system, pushing the boundaries of space exploration, we must confront not only the technological challenges, but also the deep ethical questions that accompany such advancements. The concept of faster-than-light travel and the eventual colonization of distant worlds opens a new chapter for humanity, one filled with possibilities, but also fraught with moral dilemmas that demand careful consideration. Achieving the ability to travel faster than light would unlock the doors to interstellar exploration. But what would it mean for the universe, and what responsibilities would we carry as we venture beyond Earth? We must ask, what responsibility do we have to the universe, to other potential life forms, and to ourselves? As we aim to explore the stars, how will our actions in space mirror the ethical challenges we've faced here on Earth? If humanity were to achieve the ability to colonize other planets, it would raise the question of how we would approach the resources of space. With interstellar travel becoming more of a theoretical possibility, the ethical concerns regarding resource exploitation will become more urgent. For instance, could we begin mining asteroids or extracting materials from distant moons and planets without understanding the consequences of these actions? Will we exploit these new frontiers without thinking of the long-term impact on the environments of other worlds? The Earth itself has already shown us the consequences of unchecked exploitation, and our history is marked by unsustainable practices that have led to environmental degradation. As we look beyond our planet, we must ask, are we ready to repeat these mistakes on a universal scale? Is it ethical for humanity to exploit resources on other planets for the benefit of a select few? Or should space be treated as a shared resource that all of humanity should benefit from equally? The idea of space colonization goes hand in hand with the possibility of discovering and encountering extraterrestrial life. As we expand our reach into the stars, the question of how we interact with other forms of life becomes critical. The discovery of microbial life on Mars, or the possibility of intelligent beings on distant exoplanets, would force us to reconsider our relationship with the cosmos. How do we approach the discovery of life forms on planets far from Earth? Do we have the right to interfere with or exploit these alien ecosystems for our own benefit? What if, by colonizing a new world, we destroy life that we have yet to understand? Life that may hold the key to new scientific discoveries, or even the very future of life itself. The ethical dilemma of whether to disturb or protect alien ecosystems would force us to confront a larger, more profound question. What is our responsibility to the universe and its inhabitants, even if they exist in the most remote corners of space? While the exploration of space might seem like a noble pursuit, the ethics of colonization would involve navigating complex social, economic, and political landscapes. If space becomes the next frontier for human settlement, who decides who gets to go? Will space be divided among the wealthy, or will the benefits of space colonization be available to all? Will there be equity in the distribution of opportunities to explore and settle new worlds? Or will only the privileged few get to benefit from the wealth of resources found beyond Earth? These are questions that humanity will have to answer as we prepare for a future where off-world living becomes a possibility. The potential for space colonization presents an opportunity to rethink the systems of power and wealth that exist on Earth. But it also brings the risk of repeating the same inequities that have plagued our history. Moreover, the question of mental health and psychological well-being will become paramount as humans begin to live and work in space for extended periods. The psychological impact of long-term space travel is a critical factor to consider when planning missions to distant planets or moons. The isolation, confinement, and lack of direct contact with Earth could have serious effects on astronauts' mental health. How do we ensure that future generations of space travelers living in isolated colonies light years away from Earth remain emotionally and mentally stable? The challenges of depression, anxiety, and isolation will be profound as humans face the psychological toll of living in a harsh, unfamiliar environment far from everything they know. These challenges will not only affect the individuals embarking on these journeys, but also the societies they will create. How will human cultures evolve in the absence of Earth's grounding influence? How will families form, relationships develop, and traditions take shape on distant worlds? Another pressing ethical issue is the role of artificial intelligence in space exploration and colonization. As we develop more sophisticated AI systems to assist with navigation, life support, and decision-making in space, we must ask, how much control should we give to AI? Should AI be involved in decisions about space exploration and colonization, especially in environments where human survival depends on the machine's performance? At what point does AI autonomy cross the line from helpful assistant to potential threat? There are also concerns about the ethics of using AI to run entire space colonies, or make decisions about the use of space resources. As we continue to develop AI, we must ask ourselves if these machines will respect human values, or if they will act in ways that are counterproductive or even harmful to our long-term survival. The ethical implications of space colonization also intersect with broader philosophical questions about humanity's place in the universe. If we succeed in colonizing other planets, how will this affect our sense of identity and purpose? Will the human spirit remain the same if we spread out across the stars? Will we still think of ourselves as Earthlings, or will we identify as citizens of the galaxy? As we begin to look towards space as our future home, we must also ask, what makes us human? Is it our connection to Earth, or is it something deeper, something that transcends the physical world we've come to know? In many ways, space colonization forces us to confront our own identity as a species and to ask what we truly value in our existence. As we venture farther into space, we must recognize that our actions in the cosmos will have long-lasting consequences. Our approach to space exploration, colonization, and interstellar travel must be guided not just by technological ambition, but by ethical considerations that place the well-being of all life, human and alien, at the forefront. The choices we make today as we embark on this next chapter of exploration will shape not only the future of our species, but also the future of the universe itself. As we venture further into the unknown, toward the stars and distant galaxies, it's not just our technology that will be tested, it's our very human nature. The quest to travel across light years of space, to colonize planets and moons, and perhaps even to establish humanity's foothold in other star systems, will have profound psychological and philosophical consequences. Space travel will not only change our relationship with the universe, it will transform what it means to be human. As we send people far beyond Earth, we will need to understand how isolation, alien environments, and the vast distances between us and home will affect the human mind. We must also consider how these journeys will reshape our identity, our society, and our place in the cosmos. The psychological toll of long-term space travel cannot be understated. We've already seen the effects of prolonged isolation on astronauts aboard the International Space Station, ISS. The ISS, in orbit above Earth, is only about 400 kilometers from the surface, and yet astronauts on extended missions often report feeling disconnected from Earth. Imagine the psychological effects of living on a planet millions or even billions of kilometers away from our home. The isolation and loneliness of long-term space travel will be a significant challenge. With no sunset, no changing seasons, and no earthly connection, astronauts will face profound feelings of homesickness and detachment. It is already known that astronauts aboard the ISS can suffer from sleep disturbances, irritability, and mental fatigue due to the lack of natural rhythms and the constant exposure to the artificial environment of space. One of the most profound challenges will be adjusting to a completely alien world. Just as astronauts on the ISS must adapt to the zero-gravity environment, future space explorers will have to adjust to the harsh conditions of alien planets. Planets like Mars, where the gravity is only about 38% of Earth's, will have a huge impact on human health over long periods. Astronauts will likely experience muscle atrophy and bone loss due to the reduced gravity. But it's not just the physical toll that will be a concern. The psychological effects of adjusting to these alien environments will be immense. The lack of familiar landscapes, the absence of Earth's blue sky, and the constant artificial habitat could lead to cognitive dissonance, making it harder for astronauts to form meaningful connections to their environment. In extreme cases, this could even lead to psychological breakdowns or an inability to adapt to the space station or colony. It's not just the isolation and environmental changes that will affect human psychology. The vast distances involved in space exploration will also have a significant impact. When we send humans to other planets, or even interstellar missions to distant stars, the time delays involved will make real-time communication impossible. A message sent from Earth to a spacecraft traveling at a significant fraction of the speed of light will take years, if not decades, to reach its destination. This delay will prevent immediate support from Earth-based teams. Astronauts will have to rely on autonomous decision-making systems and self-sufficiency, learning to handle problems without the ability to reach back for help. The mental fortitude required to endure such isolation, compounded by the emotional strain of being so far from home, will test the limits of human endurance. In addition to psychological factors, there are deep philosophical questions that will arise as humanity moves into space. As we venture out to colonize distant planets, we must ask, what makes us human? Is it our connection to Earth, our shared experiences as a species, or is there something deeper, something that transcends our physical origins? For generations, humanity has been shaped by our environment on Earth. The gravity, the atmosphere, the cycles of day and night, the nurturing ecosystems that provide sustenance. But what happens when we leave that familiar environment behind? Will the act of leaving Earth alter our human identity? Will we still think of ourselves as Earthlings? Or will we begin to define ourselves as interplanetary beings, perhaps as citizens of the stars? As we move farther from Earth and establish colonies on Mars, the Moon, or distant exoplanets, we will need to rethink what it means to belong. The first generations born on these distant worlds will have a profoundly different experience of being human. They will grow up in artificial habitats with no memory of Earth, and will likely have never felt the warmth of the sun or experienced Earth's natural seasons. Will they identify as Martians or as something else entirely? Will their language, culture, and even their sense of self be shaped by the alien environment in which they were born? Humanity is evolving, and the very act of leaving Earth will likely accelerate that evolution, shaping new forms of human existence that are connected not by a planet, but by the common experience of living among the stars. One of the most significant impacts of interstellar travel and space colonization will be the development of human societies in space. Colonies on distant worlds will face unique social challenges that Earth-based societies cannot fully anticipate. As we move away from the social structures and systems that have existed for thousands of years, we will need to develop new ways of living together. How will governance work in a space colony? How will we maintain social order in a closed environment where resources are limited and the psychological pressures are extreme? Will we carry forward the inequalities and social hierarchies of Earth? Or will space exploration give us an opportunity to create more equitable and just societies? These are questions that cannot be answered today, but they must be considered as we look toward the future. The social evolution of humanity in space will be just as important as the technological advancements that allow us to get there. As we extend humanity's reach into the stars, we must ask ourselves, what kind of society do we want to build in the cosmos? Will we continue to repeat the mistakes of our past, or will space provide us with the opportunity to create a new era of cooperation, peace, and sustainability? Perhaps the most profound philosophical question we must confront as we embark on interstellar exploration is, what is our ultimate purpose in the universe? For centuries, humanity has looked up at the stars, wondering whether we are alone in the cosmos. The potential for contact with extraterrestrial life, for exploring distant worlds, and for pushing the boundaries of human achievement may provide us with answers to questions that have haunted us for millennia. But the act of venturing beyond Earth will also prompt new questions about our place in the universe. Are we simply explorers, seeking to conquer new frontiers? Or is there a deeper philosophical purpose to our journey? A cosmic calling to understand the nature of existence itself? As we move into space, we will undoubtedly face challenges that we can't yet imagine. But in doing so, we will be forced to confront the essence of humanity, what we are, what we value, and what we hope to become in the vast expanse of the universe. The future of space travel is not just about the technology we use. It's about how we evolve as a species and how we redefine ourselves as we take our first steps into the cosmos. As we stand on the cusp of an extraordinary era in human history, with the possibility of interstellar travel and space colonization within reach, it's essential to step back and ask, what kind of future do we want for humanity? Our advancements in space exploration are not just about discovering new planets, mining asteroids, or establishing colonies on distant worlds. They represent a profound shift in humanity's place in the cosmos. For the first time, we're looking beyond our planet to become a multi-planetary species. And with that comes an immense responsibility, one that goes far beyond technology, science, or even the challenges of surviving in harsh environments. At the core of this responsibility lies the question of how we, as a species, will choose to shape our destiny as we expand into the stars. The possibilities are endless, but so are the ethical dilemmas we'll face along the way. As we venture out to colonize other planets, interact with alien environments, and explore the unknown, we must consider the impact of our actions on the universe around us. One of the most pressing ethical considerations for humanity's future in space is the concept of interplanetary expansion. If we establish human colonies on Mars, the Moon, or other celestial bodies, we will have to ask ourselves, are we prepared to take responsibility for these worlds? As we develop new technologies and begin sending humans to distant planets, we must also consider how our presence will affect those environments. Much like how European colonization affected the New World, space colonization could lead to unforeseen consequences. One of the major ethical concerns is the potential harm to alien ecosystems. If we encounter life on another planet, whether it's microbial life on Mars or more complex organisms on exoplanets, how should we act? Should we leave these alien worlds untouched, or is it our responsibility to study, exploit, or even colonize them? The discovery of life elsewhere in the universe raises important moral questions about whether we have the right to interfere with or alter ecosystems we do not fully understand? Could our very presence lead to the destruction of life we haven't even begun to comprehend? Or, in the pursuit of scientific knowledge and human survival, will we prioritize the exploitation of resources, potentially at the expense of other life forms? The ethical challenges of space colonization will force us to confront these questions. How do we balance the survival of our species with the integrity of the universe we're entering? How do we ensure that humanity's exploration of space doesn't repeat the mistakes of the past, where exploitation, environmental destruction, and colonialism were the order of the day? Space ethics must become a core focus of any future space agency or private company that aims to take part in off-world expansion. As we look toward the future of space colonization, one of the most pressing concerns is how to build sustainable colonies on other planets. The challenges of life in space are immense. The need for life support systems, food production, water recycling, and energy generation. Mars, for example, presents a particularly difficult challenge, as its atmosphere is thin and lacks breathable oxygen, and its surface temperatures are extremely cold. Colonists will need to create self-sustaining ecosystems that provide everything needed for survival: water, food, shelter, and energy, all within an environment that offers none of the comforts of Earth. This brings up an important ethical question. Can we truly live sustainably off Earth? The cost of sending people and equipment to space is enormous, and creating these closed-loop systems is no easy feat. Do we have the right to pour such vast resources into building colonies far away from Earth, when so many pressing issues remain here at home, such as poverty, climate change, and global inequality? As we embark on space exploration, we must ensure that space colonization doesn't come at the expense of fixing the problems we've created on Earth. Sustainability should be at the heart of any future space mission, and we must learn from our past mistakes to ensure that our actions in space are guided by an ethic of environmental stewardship. While space exploration presents enormous challenges, it also offers the potential to bring humanity together in new and profound ways. As we reach beyond our planet, the idea of humanity as a whole, rather than as divided nations or cultures, becomes more important than ever. The prospect of colonizing other planets could serve as a unifying force for our species, pushing us to work together toward a common goal: survival. Imagine a future where Earth, Mars, and other colonies work together, not as separate entities, but as a united network of human settlements across the stars. We could create a new era of cooperation, peace, and shared prosperity, built on the lessons we've learned from the mistakes of our past. Perhaps the most important ethical challenge we face is not just how to survive in space, but how to ensure that we do so in a way that reflects our best values as human beings: cooperation, respect for life, and the pursuit of knowledge. In this sense, space exploration may offer us an opportunity for global unity that we have yet to achieve here on Earth. The quest for a better future, powered by the promise of space, could give rise to a sense of shared identity that transcends national borders, racial divisions, and political ideologies. As we venture into the unknown, we may find that the true key to our survival is not just conquering new worlds, but cooperating with each other as we face the challenges of the cosmos together. As humanity begins its journey into the stars, we will inevitably face a transformation, not just in the way we explore the universe, but in the way we evolve as a species. The physical and psychological toll of living on other worlds will change us in ways we can't yet predict. The absence of Earth's natural environment, its gravity, its atmosphere, its seasons, will force us to adapt, both physically and mentally, to new realities. Our bodies and minds will have to evolve to cope with the harsh conditions of space, and future generations born on other planets may be fundamentally different from those of us who remain on Earth. Perhaps humanity will evolve to the point where those who live in space or on other planets are no longer quite the same as Earth dwellers. This raises profound philosophical questions. What does it mean to be human when our species spreads across different worlds? Will we retain our sense of shared identity or become increasingly fragmented? Each group of humans adapting to different environments in unique ways. The very act of venturing into space will reshape our evolutionary trajectory as we confront not only the limits of our technology, but the limits of what it means to be human in a universe that is vast, indifferent, and filled with unknowns. Interstellar travel is not just about expanding our physical reach. It's about expanding the very concept of what humanity is and can be in the infinite expanse of space. As humanity stands on the brink of a new era in space exploration, we are faced with the monumental task of not just reaching for the stars, but of establishing a presence among them. The future of humanity in space holds immense potential, but it is equally full of uncertainties and challenges. As we look toward the possibility of interstellar travel, colonizing other planets, and perhaps even establishing interstellar civilizations, we must begin to imagine what the long-term future of humanity will look like among the stars. What kind of societies will we build in space? How will we interact with alien life, if we encounter any? And what role will humanity play in the broader cosmic community? The idea of interstellar civilizations is one of the most exciting yet daunting prospects for humanity. Imagine a future where humanity is no longer confined to Earth, where we have successfully colonized other planets in the solar system, built cities on moons and asteroids, and ventured out to stars far beyond our current reach. The vision of a multi-planetary species is no longer purely a matter of speculation. It is a goal that is becoming increasingly feasible as technology advances. And the idea of interstellar civilizations is not just about surviving, it's about thriving. It's about creating vibrant societies that are self-sustaining, cooperative, and innovative. Societies that can survive in the harsh environments of other planets while maintaining a sense of human identity and culture. But while the technical challenges of interstellar travel remain vast, there are other philosophical and sociological questions that will define how humanity shapes its future in space. The colonization of other worlds presents an opportunity for humanity to rethink how it organizes itself. What will life be like in space? Will space colonies on distant planets and moons develop their own identities separate from Earth? Or will they remain interconnected, dependent on Earth for resources, knowledge, and support? It's possible that, over time, space colonies will evolve into their own unique cultures, each shaped by the distinct conditions of the worlds they inhabit. For example, a colony on Mars will develop in response to the low gravity, the harsh radiation, and the scarcity of resources. Meanwhile, a colony on a distant exoplanet may be shaped by the local star's radiation, the planet's atmosphere, and the presence of alien life, if it exists. In this way, the vision of humanity in space is not just about exploring new frontiers. It's about adapting and evolving to fit into new environments. Environments that are drastically different from the Earth we know. This process of adaptation could lead to the rise of new forms of human society and new ways of thinking about what it means to be human. Over time, as these colonies grow and become more self-sufficient, they may form their own governments, economies, and cultural identities, distinct from those of Earth. The question of what it means to be human in space will become even more complex as future generations born on distant planets develop their own unique experiences and perspectives. One of the most pressing questions about interstellar civilizations will be the relationship between Earth and its colonies. Will Earth remain the center of human civilization? Or will future generations see Earth as simply one planet among many in the human diaspora? In a universe with trillions of stars and potentially billions of habitable planets, Earth could become just another member of the interstellar community, rather than the cradle of all humanity. This shift in perspective could have profound implications for how we view ourselves as a species and how we interact with the rest of the galaxy. One of the most exciting and potentially challenging possibilities for the future of humanity is the encounter with extraterrestrial life. If we were to discover alien civilizations or microbial life on other planets or moons, it would change our understanding of the universe and our place within it. But how should we approach this discovery? What ethical guidelines will govern our interactions with alien life? Will we treat these life forms with the same respect and dignity that we would expect for ourselves? Or will we see them as resources to be exploited for our own benefit? The discovery of extraterrestrial life, whether microbial organisms on Mars or intelligent civilizations on distant exoplanets, presents a moral dilemma unlike anything we've ever encountered. Our history on Earth is marked by the displacement and destruction of indigenous cultures and ecosystems, and the colonization of new worlds has often been accompanied by violence and exploitation. What happens when we encounter a form of life that is alien to us? One that may be as intelligent or as complex as we are. Do we have the right to colonize their world? Do we attempt to coexist with them? Or do we see them as competition or even threats to our survival? These questions are not just speculative. They are real concerns that we must prepare for as we extend our reach into the stars. The ethical frameworks that guide our actions in space will need to consider the rights of extraterrestrial life forms, whether we encounter them as microbes or intelligent beings. As we explore the universe, we must ask ourselves, what kind of civilization do we want to be? Will we respect life on other worlds, or will we be driven by the same imperial instincts that have shaped our history on Earth? It is crucial that we develop international treaties and ethical guidelines to govern our interactions with any form of alien life we may encounter. The potential for peaceful coexistence with extraterrestrial civilizations will depend on our ability to act with humility, respect, and understanding, qualities that humanity has struggled to exhibit on Earth, but that we must embrace as we reach out into the stars. As we look toward the future of humanity in space, it's important to remember that interstellar travel will not just be about the technology that gets us to distant stars. It will be about the society we create along the way. The colonization of new planets and moons will require cooperation, collaboration, and shared goals. It will require us to work together as a species, to learn from the past, and to build societies that are just, equitable, and sustainable. The vision of a multi-planetary civilization offers a glimpse of the potential for humanity to thrive in the cosmos. But it also forces us to ask hard questions about what we are willing to sacrifice and what kind of future we want to build. As we explore distant worlds, we must remain grounded in the understanding that our future as a species will depend on how well we adapt to these new environments, how well we coexist with other life forms, and how well we manage our resources to ensure sustainability for generations to come. Humanity's place in the universe is still being written, and space exploration is just the first chapter of a much larger story. The choices we make today, the ethical principles we uphold, and the goals we set for ourselves will determine whether we become a species that conquers new worlds or a species that coexists peacefully with the cosmos. The potential for interstellar civilizations is vast, but it's up to us to shape our future, to write the story of humanity in the stars, with compassion, respect, and a deep understanding of our responsibility to the universe and all of its inhabitants. As we continue our journey into the cosmos, the quest for interstellar travel remains one of humanity's greatest challenges and greatest aspirations. Despite the immense distances involved, the idea of traveling to distant stars is not just a dream for the distant future. It is an idea that has sparked technological innovation and scientific curiosity for centuries. Achieving interstellar travel will require breakthroughs in propulsion systems, energy generation, and sustainability, areas where cutting-edge research is already underway. The path to the stars will not be easy, but humanity has a long history of pushing boundaries and achieving the seemingly impossible. Today, we stand on the cusp of technological advances that could transform space exploration as we know it. First, we must look at the current state of space travel. Right now, most of our space missions are limited by chemical propulsion, the method by which rockets expel mass to generate thrust. While this method has proven effective for sending spacecraft to the Moon, Mars, and other bodies in the solar system, it is nowhere near fast enough to achieve interstellar travel. For example, the Parker Solar Probe, which is currently the fastest human-made object, travels at around 700,000 kilometers per hour. This is incredibly fast compared to anything on Earth, but when you consider that the nearest star, Proxima Centauri, is over 4.2 light-years away, even at this speed, it would take thousands of years to reach it. Clearly, we need a new approach, one that will allow us to break free from the limitations of chemical propulsion and achieve the speeds necessary for interstellar travel. One of the most exciting developments in the search for faster space travel is the concept of nuclear propulsion. Nuclear fusion, the process that powers the sun, has the potential to provide an almost limitless source of energy for spacecraft. In a fusion-powered engine, atomic nuclei would fuse together, releasing immense amounts of energy. This type of propulsion system could dramatically reduce the time it would take to reach distant stars. Theoretically, a fusion-powered spacecraft could travel at a significant fraction of the speed of light, perhaps up to 10 to 20% of light speed, which would allow us to reach Proxima Centauri in as little as 40 years. However, despite the incredible potential of nuclear fusion, we are still in the early stages of developing fusion technology. For fusion propulsion to become a reality, we would need to master the technology to control and sustain nuclear reactions in a way that provides continuous and efficient thrust. We are still working on achieving controlled nuclear fusion for power generation on Earth, and it may be several decades before we see fusion reactors powerful enough for space travel. An alternative to fusion propulsion is nuclear fission, which involves splitting heavy atomic nuclei to release energy. NASA's fission-based nuclear thermal propulsion systems are already being developed to send missions to Mars more efficiently. Nuclear thermal propulsion uses the heat from a nuclear reactor to heat a propellant, such as hydrogen, which is then expelled at high speeds to generate thrust. While nuclear fission may not get us to the stars in the near future, it holds promise for shorter-term missions, such as traveling to the outer solar system or to the Moon and Mars, with greater speed and efficiency than chemical rockets. While nuclear propulsion systems offer tremendous potential, there are still significant challenges to overcome. Aside from the technical hurdles of creating and controlling fusion and fission reactions in space, we must also address concerns about the safety of nuclear materials in space. For example, sending nuclear reactors into space could pose risks if an accident occurs during launch, and the ethical implications of using such dangerous technology must be carefully considered. Beyond nuclear propulsion, another promising area of research is light sail technology. A light sail is a spacecraft propulsion method that uses the pressure of light, photons, to push a thin, reflective sail to accelerate the spacecraft. This concept is the basis for Breakthrough Starshot, a project that aims to send small, lightweight probes to Alpha Centauri, the nearest star system, using powerful laser beams. In theory, a light sail can be accelerated to speeds up to 20% of the speed of light, which would allow us to reach Alpha Centauri in about 20 years. While Breakthrough Starshot is still in the early stages, it represents one of the most promising methods of interstellar travel for the future. By using lasers to accelerate light sails, we can bypass the need for traditional propulsion systems, relying on beams of light to achieve faster-than-light travel. This idea could one day enable us to explore distant stars, exoplanets, and other galaxies. But like other technologies, it faces challenges. Building the laser infrastructure to provide enough energy to accelerate light sails to significant speeds is a major technical hurdle, and it remains to be seen if we can create the laser arrays powerful enough to propel these sails. Another fascinating possibility for faster space travel is the concept of antimatter propulsion. Antimatter is the opposite of regular matter. When the two meet, they annihilate each other, releasing vast amounts of energy. In theory, antimatter propulsion could provide extremely efficient and powerful thrust for spacecraft, enabling them to travel at a significant fraction of the speed of light. However, antimatter is incredibly difficult to produce and contain. It currently takes more energy to create antimatter than we could get out of it, and the technology needed to store and manipulate antimatter is far beyond our current capabilities. Despite these challenges, antimatter propulsion remains a long-term goal for space exploration. If we can solve the problems of producing and storing antimatter, it could open up a new era of fast, efficient space travel, allowing us to reach distant stars in a matter of years, not millennia. The development of antimatter propulsion could revolutionize not only interstellar travel, but also how we approach space exploration in the future. As we work toward interstellar travel, it's clear that artificial intelligence, AI, and autonomous systems will play a crucial role in the success of space missions. AI could assist in navigating spacecraft, analyzing data from faraway worlds, and making critical decisions when communication with Earth is delayed by years. Given the vast distances of space, real-time communication will be impossible for missions beyond our solar system. AI will be our eyes, ears, and brains in deep space, ensuring that missions continue smoothly, even in the absence of human oversight. Moreover, autonomous systems will be essential in maintaining space colonies. AI will likely oversee life support systems, resource management, and even farming to ensure that human colonies on distant planets are self-sufficient. AI-powered robotics will handle tasks like building infrastructure, repairing equipment, and exploring alien environments, making it possible to sustain life in space without relying on Earth-based resources. The integration of AI and autonomous technology will redefine how we approach space exploration and colonization, making interstellar missions and long-term stays on other planets more feasible. However, this raises important ethical considerations. As we entrust more control to AI, how do we ensure that human values and ethics are incorporated into the decision-making processes of these systems? Who is responsible if an autonomous system makes a critical error in space? The journey toward interstellar travel is undoubtedly one of the most ambitious endeavors in human history. While the speed of light remains an ultimate limit, emerging technologies such as nuclear propulsion, fusion energy, light sails, and AI systems are paving the way for faster and more efficient space exploration. Though many of these technologies remain in the early stages of development, they represent the next frontier of scientific discovery and technological innovation. As we push toward the stars, we must continue to address the technical challenges, ethical dilemmas, and philosophical questions that arise. Humanity's future in space is not just about reaching the stars. It's about shaping the future of life beyond Earth and ensuring that we embark on this journey with responsibility, wisdom, and vision. As we conclude our journey through the incredible concept of the speed of light and the possibilities of interstellar travel, it's clear that the future of humanity is boundless. The mysteries of space, time, and light continue to challenge us, but they also offer us endless potential for discovery, exploration, and growth. As we push the limits of technology and space exploration, we must remember that the universe is vast, and our journey has only just begun. If you found this journey through the cosmos inspiring and fascinating, don't forget to subscribe to Science for Sleep, where we dive deep into the wonders of the universe, unravel mysteries, and explore the unknown. Join us on this adventure, and together we'll explore the next frontier of human knowledge and discovery. Before you drift off into your own dreams, take a moment to reflect on how the universe operates, how every star and planet is governed by the speed of light, and how space-time itself is shaped by the laws of physics. The same forces that govern the vast distances of space are the ones that shape our everyday lives, reminding us of the incredible complexity and beauty of the world we live in. As you relax and let your mind wander, remember that the stars are waiting, and so is the next great adventure. Sleep well, and let the quiet mysteries of the universe guide you into a peaceful slumber. Good night, and may your dreams be filled with the wonder of the stars, as we all journey together through the vastness of space.